4 episodes ago, we built one unit and wrapped a loop around it. Run the input forward, score it with a loss, push the error backward, take one small step, and repeat. The heart of that loop was a single quantity, the residual, the prediction minus the target. Episode 2 paid a debt that inductive biases deferred 6 times. We derived the backward pass by hand, and then we checked it against a finite difference, so we never had to trust it on faith. Episodes 3 and 4 reused that exact backward pass, once for a softmax across many classes, once for a deep stack that learns exclusive, and we never changed a single line of it. Today we cash it in, and we find out just how far that one backward pass reaches. 5 different jobs, 1 unchanged spine. 1 body, 5 heads.
Hold on, 5 different tasks from a plain yes or no all the way up to learning your own uncertainty, and you are telling me the backward pass never changes. Surely each one needs its own gradient math, its own derivation, its own bugs to chase.
That is exactly the bet, and it pays. Keep the body fixed, a linear layer, a tan, another linear layer. It takes an input and produces raw numbers, the logits, and it has no idea what they mean. To the body, they are just the outputs of some arithmetic. Look at the backward method. It walks those layers in reverse, and the very first thing it asks for is the gradient from the loss, that one line where it calls the losses grad. Everything after that line is chain rule through layers we already wrote and already checked. So the only thing we will swap, task to task, is the head that supplies that first gradient. Change the head, and you change the meaning of the whole network without touching the body at all. Start easy, predict a real number. Swap the head to mean squared error, and fit the curve y equals sine of x with that same little body, a linear layer into a tan into a linear layer out. Here is the whole head, 3 tiny methods, and the one that matters is grad. Its gradient is the raw output z minus the target y. That is the residual, how far off you were, and nothing more. And notice the prediction here is just the raw output itself. This head uses the identity link, so the number the body computed is the number you report. No squashing, no sigmoid, nothing in the way.
But squared error is not a probability at all. The last 3 episodes were all about probabilities and cross-entropy. How is this suddenly the same machine?
Because the network never dealt in probabilities to begin with, the loss did. Under the hood, squared error is the negative log likelihood of a Gaussian with constant variance. You are still doing maximum likelihood. You just assumed a smooth bell curve of noise around each target, the same width everywhere. Minimizing the squared error is just maximizing that likelihood, written as a penalty. So we call the same fit method, the same mini batch gradient descent, and it runs the same forward and the same backward we already have. The sine curve comes out, and not one line of the body changed. Now counts how many events happened. Arrivals at a queue, photons on a sensor, defects on a wafer. Swap the head to the Poisson negative log likelihood. The body still emits one raw number, but now we read it as a log rate, and the predicted rate lambda is the exponential of that number, which is positive no matter what the body hands us. And the gradient, the exponential of z minus the target y. That is the rate lambda minus the count y, the predicted rate minus the observed count, the residual again. Different head, different link, exact same shape.
Why not just use squared error on the counts? Counts are numbers too, and squared error already works.
You can, and it will quietly lie to you. Squared error assumes the noise is symmetric and the same size everywhere. And because the identity link is unbounded, it will happily predict a rate of -3, which no count can ever be. The log link makes the rate positive by construction, and the Poisson builds in the fact that the spread grows with the mean. Rare events barely wiggle, common ones vary a lot. That is exactly how counts behave. Same body, same backward pass, a head that finally tells the truth about counts. Last head, and the most interesting. So far, every model gives you a single answer and no sense of how much to trust it. Let the model say not just what, but how sure. Give the body 2 outputs instead of 1. The first is the mean mu, read straight off as before, and the second passes through soft plus to a positive scale sigma. Soft plus keeps sigma positive smoothly, with no clamping and no special cases. The gradient on the mean is the mean mu minus the target y, divided by sigma squared. It is the residual again, now scaled by confidence. When the model claims to be certain, sigma is small, and dividing by that small number makes the very same mispush far harder on the mean. But the head also returns a second gradient, through soft plus, that pushes on the scale itself.
But nobody handed it labels for the uncertainty. The data only says what happened, not how sure to be about it. How does it learn that with no answer key?
The likelihood is the answer key. Claim tight certainty and then get it wrong, and the loss punishes you hard through that division by a small sigma squared. Hedge instead, with a huge sigma on an easy point you could have nailed, and the separate log sigma term charges you rent for the vagueness. Caught between those two pressures, being punished for false confidence and taxed for laziness, the network settles on honest error bars learned from the same data and nothing else. The mean side is still a residual, just scaled. The scale side is the calibration bill. The same backward pass carries both. So line them up. 5 heads, 5 gradient methods, pulled straight from the source and set side by side. Binary cross-entropy hands back the sigmoid of z minus y. Softmax cross-entropy hands back the probability vector with 1 subtracted at the true class, which is p minus y. Squared error, z minus y. Poisson, the exponential of z minus y. Gaussian is the honest wrinkle. It returns 2 numbers. The mean channel is the mean minus y divided by the variance. The scale channel is the pressure that learns how uncertain the model should be. So the pattern is real, but not sloppy. 4 heads are direct residuals. The Gaussian mean is a residual scaled by confidence, and the second channel pays for calibration.
That cannot just be a coincidence that they all collapse to the same shape.
It is not luck, and this is the punchline of the whole series, but we should say it precisely. These losses are negative log likelihoods, so training the network is doing maximum likelihood. Bernoulli, categorical, Gaussian, and Poisson are not random scoring rules. They are probability models for different kinds of data. When the output link matches the distribution, the residual-shaped gradient is a theorem, not an accident. And when the head needs more than one number, like Gaussian uncertainty does, it simply hands back a longer gradient vector. The same backward pass from episode 2 does not care. It carries that vector back through the body. One derivation, paid for once, spent honestly. Step back and look at what we built. The body computes numbers. The loss chooses what those numbers mean, and quietly, what noise you assumed in the world. That second choice is the one people forget. Choose the right head and the same clever network is a classifier, a regressor, a count model, a calibrated forecaster. Choose the wrong one and that same network hands you confident nonsense. Negative counts, symmetric noise on a lopsided world, certainty it never earned. The network cannot warn you, because to the body every output is just a number. The head is where the meaning, and the mistake, lives. This is the mechanics behind inductive bias's opening claim. The network computes numbers, and the loss decides what they mean. That series argued it from meaning. This one earned it from code.
So that split from episode 1, logits on one side and the loss on the other, the one that felt like pure bookkeeping. That was the whole design the entire time.
That was the whole design. And we do not take it on faith. Watch the series signature one last time, now across all 5 heads. For each one we run the gradient check, the analytic gradient from our backward pass, against a numerical finite difference. Binary, categorical, real, count, and uncertainty. Every worst relative error lands around 1 part in 10 million. 5 heads, all green. 1 backward pass, verified 5 times over. That is the core so far. 5 episodes and no autograd, no magic anywhere in them. A body that computes numbers, heads that assign meaning, and one backward pass that trains them all, checked at every step by a finite difference we wrote ourselves. Everything you saw was pure Python, standard library only, small enough to read in an afternoon. From here, the same little body goes further. The next episodes pick up the debts inductive biases still owes, convolution, recurrence through time, and a language model assembled from the parts we already have. We build each one from scratch too, and check every gradient. See you in the next one.